All right. And so now we get to the best part of the show. I get to introduce the speaker. So Dmitry Chuyko, and I hope I'm saying that properly. These talks are the ones that I usually get the most out of, because I do a lot of enterprise development, and I don't get to hear about all the mechanical sympathy type of things. Where you're talking about working with the hardware, optimizations on hardware, because when you're a Java developer, you just assume, like, I'm just writing the code, it's going into bytecode, and I can just ignore all the stuff that's happening under the surface. But the reality is a lot of interesting things are happening there, and a lot of those things can impact the companies you work for in interesting ways. So it's kind of important to keep your eye on the hardware side and the architecture, and that's exactly what Dmitry's going to be talking about tonight. He's an OpenJDK committer. He speaks publicly, so you're getting this direct knowledge from someone that works on the project, which is, in my opinion, the best people to be talking to. So without further ado, Dmitry, I'm going to make you the host and turn over the screen share to you.
Well, thanks for the great introduction. So our topic today is Java and ARM. Well, it's not so new, but still we get used to x86 hardware, then we run our applications, both desktops, IoT sometimes, and of course in our clouds on our servers. This is a kind of a recurrent topic right now, because I used to start talking about that, then there was some break, and I'll cover that material here. But now it's a time for a new generation of hardware and probably some new stage in that development. So it's interesting to see what changed now. And this is, I would say, on scale of maybe 4 years. So what happened during that pandemic year and years around it. So I'm talking about this because really, yeah, as Bob said, I participate in development of different features, specifically in this port as well, in port for ARM hardware and port of OpenJDK. BellSoft is one of the most active enterprise contributors to OpenJDK and participates in many activities around it. And not just in OpenJDK, but also GraalVM project, and there is now a new connection between these projects. So we try to keep all our customers' production safe by providing commercial support and different nice options to get your JDK builds or base container images for microservices and different kinds of applications. Yeah, you can contact me easily or read our blog that contains some articles about Java. So why am I showing you this picture with outdated devices with big frames? Well, because even at time when devices looked like this, they mostly were powered by ARM CPUs. And if we take modern devices, the situation is still the same. There are growing competitors. Probably they will have some chances in the future, but for now, this market is dominated by ARM. And this acronym can be translated differently. Well, you can see a couple of variants here. But basically, there's a company named ARM that creates CPU designs and maintains the architecture, the ARM processors architecture. And then I started to work in this area, or slightly before that. In 2013, the estimation of ARM devices produced in the world was like 30 billion. And by this year, so this is a number from Q3 2022, it's like 250 billion. So the growth is enormous. And how we would perceive this architecture, ISA, instruction set architecture? Well, ARM itself defines it as a way to communicate between programs and hardware. So we need protocol, we need to specify how we create binary code for a certain silicon. And if we look to even more details, we will see that there's a company and there are profiles and there's an architecture called capital ARM and having a logo of lowercase ARM. But this architecture has different profiles, and for us the most interesting profile is called application profile. This is something suitable to run virtual machines like Java virtual machine, to run real programs that we are used to see on desktops and servers. And that architecture has numbered versions. So it evolves and there are fixed versions, just like language specification for Java, for example. And different devices implement different versions of the architecture. In that architecture, there are two execution states. So basically the same silicon can work in different states. Then we boot for example, our development board. Sometimes it's able to work in either 32-bit mode or 64-bit mode. An example is Raspberry Pi, for example. And this AR64 execution state operates A64 instruction set. That's the name that you can find in the specification. And there's also a code name ARM64 not being used officially, but being used by different projects like Linux kernel, or it was used in OpenJDK as well. So if you have Java 8, the port there is still called ARM64. So ARM does some work about development of specifications for the instruction set. So this specification can be licensed, or some custom IP designs can be licensed. There are multiple options. Different organizations take different approaches to that licensing, and it depends on the kind of the organization, like either it's an educational institution or is it an enterprise. So it all depends. There are many options, and it also depends on the profile that I've mentioned. So in this architecture, there are many profiles, and you see that application profile is kind of a powerful one, right? Because it's not something that we would expect on microcontrollers. It's something that we would expect from a more powerful silicon. And there are two active and interesting branches here that actually operated 32-bit mode and 64-bit mode instructions. What's also interesting about the hardware that we can find is that ARM actively uses and promotes big. LITTLE architecture structure. Then low power or low capability cores are combined with high capability cores. And here are just some ones from the very recent designs. And they're expected to be found in new chips. Actually, I will mention some products that already incorporate that cores. And a fun fact about this is that in a single system, different in some moment in time, different CPUs can operate in different modes. That means we temporarily may not be able to run some 64-bit mode, 64-bit code on certain CPUs in the system because they operate in 32-bit mode. That's theoretically possible. well, probably it's not the case for us Java developers, but still it's interesting. And of course, if you think about different devices, we're sometimes interested in making our own pet projects, like building robots or some controlling some electrical toys. And that's a popular thing. In devices that are in a high-end class, high-end part of such class of devices, we can run Java. So if we talk about Raspberry Pis 2, 3, 4, or other development boards, we can run Java on them. Different versions of Java, and we can run either 32-bit mode port or 64-bit port. And that 32-bit port still exists and being maintained. We're probably currently the most active maintainer of the port. It's not an easy task because OpenJDK has so many new fascinating projects, like Project Loom, for example, and this is a challenge to keep it working or be compatible with the specification. But you can execute different operating systems in that mode, and you can run Java there. And you can create very small runtimes with Java. So Java still contains minimal VM, and now it contains JLink, so you can minify the runtime very significantly. From another hand, you have great options to actually run rich UI applications there on such small devices, like rich applications with Swing or with Java effects. And it works there, and sometimes it works directly with your video buffer. So it's still the case, and you can find the recent versions of Java for that, like Liberica Embedded, for example. If you talk about minimal VM, it's really an interesting small feature. Then you can replace your full server or client VM with a VM which is much smaller, but of course you'll lose in performance. But if you really have constraints in your disk memory, it's possible. It's still possible. All right, let's look at that larger devices, and we can have a brief overview of the history here, how this specification evolved and developed. You see some dates. So the lowest scale, the axis, is dates when specification was released. So like ARM v8 first version was released in December of 2011. But in that square boxes you see some features, just some features of each version of the architecture. And on top of that, there are some core designs that were actually used in some products. But that products was released much later than specification that they implement. For example, we started to work with A53 and ThunderX, and it happened in 2017. So they weren't new, but they were still actual at that time. So you see there's a big gap between specification release and how products that implement that specification in silicon go to market. And I would say today this gap seems to be smaller than that. So some products that we see borrow features from higher specifications, or they just being released faster than 5 years gap. And that's so that Cortex A53, A73, for example, that are ones that you'll find in Raspberry Pis. So it's still, I think Raspberry Pi 4 is A73. So Raspberry Pi 3 for sure is A53. And ThunderX was an interesting experiment. So this CPU had relatively weak cores, custom design ones, but it already had like 96 cores in one chip. And then it had the second generation that implemented newer version on specification, had much better cores and even more of them. We'll see how it looked like. And after that, in next versions of the specification, interesting additions were vector instructions that are actually optional in 8.2. And this is something that Intel has for a long time. Intel has vector instructions. It has AVX or slight weaker instruction sets. And what's interesting about ARM extension, it's an optional one, at least for that versions of the spec. So you may not, or you may implement it or not. And vectors there, they don't have a fixed length where in the specification. So your implementation is allowed to provide some vector length in silicon. And your program can determine that and adapt its code or just use some generic code that works. Like if you process an array and you have some operation that processes large chunks of that array, you can rely on some loop that does bigger or smaller chunks, but does this operation the required number of times. You just see that either you reach the end of the array or not. So this is a great idea, and it was implemented later in the chip called A64FX. And this is a chip for supercomputers. We'll have some specs later, but other designs not implemented in SVE are listed here, and they are Cortex X1, which is a powerful core used in mobile chips, and Neoverson 1, which was implemented by different CPU vendors, and this is one which is nowadays probably the most popular in clouds. So you see the spec was developed and presented in 2016, and this is our current for now. There was also a continuation of ThunderX line called ThunderX 3, but it wasn't released publicly to market. But it had even more powerful cores and even larger number of cores. But there are different trade-offs with TDP and cost and other issues. Then you see next variant of the architecture was implemented in Neoverse V1. It is an ARM design. And these are also implementations that we can see now. We'll see examples. And this is our current and our future for a year or so, I believe. And also that version of the spec was implemented in Apple Silicon in M1. So you see the desktop CPU and interesting server class CPU, they implement the same modern version of the specification. Probably it took about the same time to develop them, right? Because development teams start to work with some preliminary version of the specification, or they have early access to some results. And then, of course, we saw some upgrades like M2, which is still RV8. And finally, in 2021, ARM v9 was presented. So it wasn't what it could be 8.8, right? It was 9. And this version of spec contains extensions or describes extensions like hardware transactional memory and second version of scalable vector extension, SV2, which are very interesting. And there are silicon implementations built from that, like Cortex chips listed here. If I remember it right, they are present in the current generation, the most modern generation of Qualcomm desktop chip. I will say slightly later. And also, again, desktop and server design, Neverse N2. What's next? Well, you see, probably this fall we'll see a new spec, or maybe it happens earlier. So there are different licenses, different in silicon implementation of the spec, and you, I think, know all that companies listed here. And each year, the number of such implementations just grows. Well, we already saw mentions of this Neoverse thing. And here's the roadmap by ARM of the development of ARM's reference designs for server and HPC platforms. And here N and V series are the most interesting to us. And you see, it's bound to actual production norms that are reachable at some point in time. Like you see, the technical process being shrinked from 7 nanometers to, well, projected 3 nanometers, because we are already living in 2022 plus. So you see N1 and N2 and V1 platforms here. And N1 was kind of first in this row, and then V1 already mentioned today. And there are actual hardware chips that implement those specifications. Well, I promised to show you some history and how it started with a lot of cores. So the server that contained ARM chip with many cores in 2018 or 2019, it looked like this. It really looked like this, and many of such servers still work in big supercomputer productions, but not in clouds that we are used to. And it was fun working with that. You see so many hardware threads, while newer designs also show the increasing number of CPUs in them, increasing number, of course. Well, for the past 5 years, the ecosystem for ARM machines was developed very well. There are many operating systems supporting ARM machines, and this is the initiative started by Linaro, I think, or maybe by ARM itself. But now cloud vendors also care a lot about supporting the ARM ecosystem. It means many software as a service solutions provided by cloud vendors are compatible with ARM machines. So if you go to a cloud, you'll probably find a page that describes compatibility between, services provided by that cloud and hardware provided by that cloud. This sounds kind of obvious, but still there may exist products that are not compatible with ARM hardware. Well, I don't really know such services. And probably this is definitely something being fixed, like right now. And among operating systems, we also have Windows. We now have macOS, right? Because there's hardware running, ARM hardware running on the operating systems. And some time ago, the interesting activity that we introduced and we participated was related to performance of AR64 port, performance of OpenJDK on ARM hardware. So we worked with different hardware available at that time and tried to predict, well, how it could work on prospective hardware. It's a separate topic on how we did that, how that optimizations look like. But basically, if we know that CPU has certain specific features, latency considerations or extensions or certain instructions that can be used, for example, for in intrinsics, in the hardware specific implementations for some methods within standard library. Well, that knowledge can be used for to have an effective implementation to increase performance. So some operations like string operations were improved over 70 times. Other even tiny operations like improvement for signum function that brought interesting results for workloads like Lucene. And this is still a work being continued, so the major change were delivered in this job into JDK 11. And JDK 11 updates still got backports up to the very recent time, backports of new functionality, new improvements from newer JDKs. I would say it doesn't happen now, so JDK 11 is kind of being slightly frozen, but there is JDK 17. So JDK 17 updates definitely get some improvements from newer JDKs. And when we talk about performance, there's a question about diagnostic of performance. And actually, all tools that we are used to, they work. Well, you see here some examples of async profiler diagnostics, or we can run JFR, we can as well run perf and perf map agents on ARM machines. And by the way, here you see an IDE, and of course IDEs work as well. So we can run Java development IDEs on different machines, even on relatively weaker one. And I had fun experience running Eclipse IDE on Jetson Nano. This is a board that combines 4 ARM CPUs and some NVIDIA card, and it's able to perform online processing of your video streams, and it can be combined with Java and JavaFX. And it was able to run Eclipse pretty well. And by the way, these boards, as powerful as servers were powerful in the early days of Java. And then you run some IDEs, like you run JetBrains products on ARM machines, and you know that JetBrains runtime is being supported by BellSoft. So here's where we apply that experience as well. ARM sometimes is different even for Java development. Yes, as Bob mentioned, we write code and we don't care. But if you write it not entirely correctly, it still may work correctly on some architectures like x86. And we probably tested it there already, but then we bring that code to ARM platforms. And we see some concurrency effects, which are not bugs. They are by design implementation of your how your CPU works. So it's described in that ARM specification, and it is expected for performance. It's expected from a chip to perform certain optimizations in a way how your program is being executed. So here are some results from all times, but you will see much more interesting results on the newer hardware because it's faster, and it means it performs even more optimizations. And that optimizations are allowed by Java memory model, but we just don't observe that effects on the different hardware like x86. So let's get back to that chips and their roadmaps and what's being implemented when. Well, you saw some implementations that are kind of be used in mobile designs or in some smaller boards. But of course, there are chips, top chips for clouds, like Alibaba has its own custom E10, and AWS has its own top Graviton 3. And there are special chips for supercomputing, like NVIDIA Grace is designed to be used with powerful GPUs and it's designed to have a lot of cores. And it's a very special machine. This is an HPC area where we not necessarily see Java, but it's also interesting because it shows how powerful the chips can be. So there's a big supercomputer in Japan called Fugaku, and it's built on that A64FX chips. There are many usages of that NVIDIA Grace chip. And this is the picture of the chip. And it has something around 144 hardware threads, and it can address a lot of memory, so it's an interesting machine. That's for HPC, but for generic purpose cloud computing or server computing, there are two generations of Ampere Ultra, and they basically differ in a number of cores in them. So the first design, probably displayed on this picture, mentioned 32 ARM cores, and then the number of cores raised to 80, and now it's raised to 128 cores. And this chip is interesting because you can find it in different clouds. You can find it in Oracle Cloud. You can now find such machines in Microsoft Cloud and Azure. And you can also buy a server for yourself. You can just find one of multiple vendors who produce servers and order a physical ARM server machine and use it. So that's something that has changed for a few past years, and they are now very accessible. That's one of options how cloud vendors can acquire ARM hardware. Another option is to use their own design, like Alibaba does or AWS does this. And AWS has 3 generations of their Graviton CPU. And that 3 generations are really different designs. So you see they were introduced a few year gaps and 2 years for the second generation and 2 years for third generation. But this 2021 was actually an announcement date for early access. And I think C7 instances are only available since late last year. I may be wrong here, but this is a very relatively new thing that you can get as a generically available ARM instance. And you see how production process developed. You see that specification version became newer and newer. Clock speed wasn't, it didn't increase that much because there are certain power limitations for your hardware in a data center. So it just grows with small steps, but still it grows. And of course, core types change dramatically from some generic design to design specifically developed for being effective in clouds for serious workloads. Number of cores, it already has increased. Memory protocols and memory bandwidth increased dramatically. All that leads to a very dramatic growth in performance. So the last row is a kind of speculation. So it's some ephemeral counter that you please don't use it for estimation of your any production workloads. I may lie to you here, absolutely. I'm probably doing this. As a rough estimation, AWS itself estimate the increase in performance from first generation to last generation like 7x. Here this number is like almost 10x, but still it's very impressive. For 3 years of development, you have such a great leap in performance in hardware. And you don't have to change your software because we write in Java, we have our bytecode, just please write it correctly from a concurrency perspective, test it, and that's it. You just update your operating systems, they get support for latest and greatest hardware and its features, update your Java versions, and you see both boost in your hardware performance and boost in the performance of your runtime and your operating system. I didn't mention another cloud yet, Google Cloud. There are some rumors, complete speculation. Like we may see some custom design from that cloud as well. Because of course, everyone is interested in the success of this hardware. And what's the key thing here? Why everybody cares about ARM as a server, ARM as a cloud instance? What's the point here? Well, when Graviton 2 was released, there was an interesting article, you can easily find it, like x86 massacre. So of course all measurements were done at that time, but it shows that you can save a lot of costs by using such instances. Well, different vendors, x86 vendors, Intel, AMD, of course, they also released their new versions. But at that time, and probably in many cases nowadays, there's such a great difference. Of course, your workload must be suitable and many other, mandatory conditions. But the adoption of ARM servers grows very rapidly. And it's now a significant share in all computations, in all instances in public clouds. So different vendors, different cloud providers, they have slightly different numbers, but just my perception of it. This grows, and for past few years, it grew from 3% to 8% in clouds. And the expected growth is like 10% in 2 years. The ARM service will occupy a 10% share between across all the instances. And for example, Alibaba says that by 2025, they will switch 22% of their instances to be ARM instances for the internal services and probably for their public services. And many questionnaires show that Java is very popular. So using Java on ARM instances is a popular scenario. Sometimes it's like 80%, or at least I read that for some small clouds. So this is not something entirely new. In server space, we can see it being used. But what about development? Well, you know, at some point in time, we all saw this. And it was a kind of a shocking moment because I especially like this model because it was very powerful and it has no fan and it has very good design and had M1 chip in it. AR64 chip. And we are able to use our development tools on this machine or on more powerful new versions of MacBooks or Mac Minis. We'll see why it works and how it works, but that's not the only option. Of course, there are many low-end Windows ARM notebooks. I wouldn't take them so seriously, but this year, or even last year, Lenovo X13S was released, and it contains this latest and greatest so far Snapdragon chip. This is a system on chip, which is powerful enough to compete with Intel machines, and probably this one is more powerful and more responsive than my laptop here. So, and it's able to run Linux or Windows on ARM, and this is cool. And it has also very good lifetime from battery as well as MacBooks. Other types of machines are tablets like Surface Pro, and it's fun that we use such tablets then we prepare and test our binaries of OpenJDK. So it's suitable even for that purpose. So it's a serious thing. Yeah, and there are again some rumors about 4th generation of Snapdragon chip that probably will be even more powerful. Maybe it will be RB9. I don't know. Oh, this one is already RB9. Yeah. So what about Java working on that machines? Well, we now have 3 operating system ports. Actually, 3 or more. So here you see the original one was, of course, Linux AR64, and also there was Linux ARM64, which is for Java 8. We also have that. And there are ports for Windows and for macOS, thanks Microsoft. And that ports were made in Java 16 and Java 17, and later they were also officially backported to JDK 11. here we're glad to participate because this is really an important and necessary thing to have. Well, we also have support for musl C library for Linux, which also can be considered an additional thing here. And besides of that, vendors like BellSoft can provide additional features like JavaFX support for native images or native images support at all. Like we provide our binaries for that purpose. And the product is called Liberica Native Image Kit. And sometimes you need some efforts to make swing working as well. So anyway, the important information here is that you can find such binaries. You can find such OpenJDK builds with fully working graphics, and you can have native image with working graphics for macOS, for example. So you can create an application that starts instantly and displays some rich user interface elements. But what's the point on macOS specifically, right? Because there is Rosetta 2 and we can actually run x86 binaries of Java. But there is a great difference in performance. So we made some experiments and sometimes it's more than 2x difference. So here are some few benchmarks, few Java benchmarks, and execution time is being measured. And you see that same benchmark being executed in the emulator is much slower than the benchmark being executed with a native JVM. So that's why we really need native ports for all the platforms. Well, platform-specific plays role because some features are kind of optional, right? Because the specification doesn't require you to have all garbage collector implementations. You can have only one. That's enough because there must be a garbage collector, but which one? Who cares? Well, sometimes somebody cares, and ZGC was ported for AR64 during JDK 13 time frame. There's a nice feature of more advanced atomics in R. And that atomics play a role in native code, they play a role in scalability. There's an interesting study by Ampere that they show how it plays a role in their hardware. And Red Hat made great work of bringing that atomics to OpenJDK. And in some enterprise workloads, it makes like 5% difference. So the same as many garbage collector improvements, just more advanced atomics are being used. As I mentioned, vector extension is an interesting feature in the ARM architecture. And we have also vectors in OpenJDK, Vector API. I think this is, it's still being incubated right now, so. And ARM made a great job of implementing all that intrinsics for the Vector API and made them using actual efficient instructions from the instruction set than SV is present. So when somebody tries to run a vector algorithm, or if it will be used inside the standard class library, we already have efficient implementations on the real hardware. And we now have that hardware. We have HPC hardware, but we also have server class cloud hardware. Like Graviton 3 implements that extension. It is kind of a new thing because the performance difference between so-called Neon extension and SV, they are comparable. Well, we saw that SV can be faster, but not, times faster. There's a new feature, virtual threads in Java. Implementing virtual threads requires implementing or involving some specific of your CPU. And that also works and is supported on ER64. We have native code, native libraries, binaries, and implementation of foreign function and memory API also supports ER64 because goodness could be skipped. It's still in preview, but if you enable preview, you're able to use that. Well, these are kind of advanced features, but nowadays some basic functionalities. Well, does it work in a container? Yes, it works. And we have container management systems working on different operating systems. Of course, it all works on Linux kind of perfectly, or at least we won't see a real difference there. It also works on Mac OS. We now have, for example, Docker Desktop. It has its own peculiarities. The implementation had some history of incompatibilities, but now it more or less settled, so we can just use containers. And we can use ARM desktop software and hardware to prepare our containers for our ARM cloud instances. So we just need that native container images. Well, and if we build our own images, there are multiple ways of doing that. We can create Docker file ourselves. It should always work. But there are different options. There is no correct answer here, or they all are correct. The incorrect answer is like, we don't do that, or we do something else. But the most convenient way here is to use build packs, especially if you use Spring and, if you create containers using build packs in Spring Boot, you will have containers with Liberica. And unfortunately, x86 is not supported. Oh, sorry, ER64 is not supported yet. There were some dependencies, some blockers. Probably they are now resolved, but it still takes time to have the implementation. So this option doesn't work, but other options, they work here. And for example, we can use the smallest containers, the Alpine Linux or Paquita Linux or other musl-based Linuxes. And support for such containers was brought by BellSoft with the implementation of this JEP 386. And it happened in JDK 16 and has been backported to 11, and there are also containers for 8 and other versions. So you can find small container images suitable for your ARM servers or desktops. And you can just build your container image on top of that. It's complex, or you just can try that container images, like to see how Java works. You can run JShell, or you can run and investigate what's been reported about your system. So here we run kind of a Linux container inside Mac OS, and we see that, yeah, this is some ARM processor being available for us, and system reports that information. So on top of that, we can create our Docker file and run a Docker build. And here is just one of options. You see this is OpenJDK Alpine musl container. But you also can use Liberica runtime container that's based on Alpine Linux. And this is kind of more native one. The probably wrong option here is to write from OpenJDK because this is a deprecated image. So please, if you create your container image, just base it on some known to you, some image known to you, denote exact tag, exact version, and it should work perfectly. And there's also even a cross build. So you can create containers for kind of foreign architecture. You can create ARM containers from x86 machine, and you can create x86 containers from your ARM machine. You just need this tag to be available for your target architecture. Then you run that cross build, this buildx command. Here's an example how to do that. So summarizing all this, there is now a great hardware available for us. There's a great ecosystem around ARM. So it all works, especially if we use clouds. We have cloud services, we have that instances, and we can switch to that instances in most cases, especially if we run Java programs, by simply changing the type of the instance. And OpenJDK works great on such machines. It's been highly optimized for many versions, and it becomes better and better. And then we mix our hardware during our development process. We can even make cross-development. So it's possible, and things became really easy for developers. And we still can use all our familiar development tools, which is again great. Yeah, please contact me if you have any questions or you need some extra meetup. Thank you for your attention. I will be happy to answer questions because I hope that there are questions.
Are there any questions? I know I have a few.
Great.
Oh, here you got one through chat. Are any thoughts on JDK coming to RSSC 4? RISC 4?
Maybe RISC 5.
5, sorry.
Yeah.
I don't know why I'm...
You won't believe it. It's already there. The port is integrated, so we have official, source for RISC 5 and OpenJDK 3. And there are devices, and on some devices you just can say, okay, install the package and you'll get the build. Yeah, the port has been mainly developed by Huawei. So they had their own fork initially and then integrated the port into source code. But at least from now, maybe RISC 5 devices will, occupy that niche of kind of low-end devices for IoT. So, but it can be different.
All right. I have a question. Going back to one of your slides where you were comparing performance on Intel and you were mentioning some of the unexpected differences, the interesting differences. I was trying to figure out what the numbers meant, where some of them were zeros and then there was ones on the ARM column. I think it's a little further back. Keep going.
Yeah.
It was probably at this one.
Yeah, it's not performance. It's yeah. So this is a result of JC stress test. So there are special tests designed to show or check correctness of both hardware and JVM in terms of implementing the Java memory model. So that tests, they contain multiple actors being executed in different threads.
Mm-hmm.
And that actors perform such different actions. Like you can create an object, assign some fields, and observe the result. At the same time, you kind of trying to read that object in another thread. And sometimes results can be surprising if you don't perform synchronization or you rely on some events. You observe an outcome in a different thread. And you observe different outcomes because it's a concurrent execution. And for sure, there are scenarios then certain outcomes are not desirable. Like you observe an object before you finish constructing it.
Mm-hmm.
And that's what can happen if you run on a different hardware. And you can have an incorrect Java code that relies on how things work on x86. And you won't have such a test with interesting results on x86. You never have it. But on different hardware, you actually see that outcomes.
Mm-hmm.
That's what's different about ARM. So it's not, it's not performance. It's a kind of.
Got it. So these are validations. So are the numbers that you're showing, are these the number of tests that pass? Or is it showing failures with the zeros or what? I'm just trying to figure out how to read this properly.
There are different outcomes. So here we observe two values. Like we read two values and each value can be like 0, 1, 2, 3. Right? Mm-hmm. So these are just states. And some states are never observable on x86. But there are, like for the listed machines, up to 4 cases, four occurrences of such a state. It's a low number.
Yep.
Among tens of millions of executions. So tens of millions samples at all. But among that tens of millions, we have few rare
surprises.
Yeah, events that will probably break our incorrect program in production.
Mm. No, that's interesting. So if you're not using, again, like synchronized blocks, or if you're not publishing your memory by properly declaring things,
yes,
maybe final things like that, you're saying the architecture is going to come back and bite you.
Yeah, you'll be punished. And another interesting case is then you have a correct code, but you still see unexpected results on the hardware.
Mm-hmm.
It means there's a hardware bug. And it really happened in some early days of some CPUs.
Thank you. No, that explains the chart. That's why I was just trying to get the
great question.
Gist of it.
Thank you. I just skipped it,
All right. Do we have any other questions? Okay. Well, thank you, Dmitry. And you've provided contact information, so folks do happen to think of additional questions, they know where to reach you. Is there a specific best place to reach you? Is it Twitter? Is it email?
I'm at LinkedIn or Twitter.
LinkedIn? Well, Dmitry, I look forward to chatting with you more at DevNexus.
Yeah,
should be a good time. We'll be able to get beers there. So,
all right. Thanks again.
Yeah, perfect. See you then. Thank you so much.
Bye.
All right. Thanks so much, Bob.